I'm also actually an employee of the same company that Kent works for, who, if you were here yesterday, you saw his presentation, and you know that Halcyon Molecular is a company that's working on making some amazing, new, very rapid, accurate genome sequencing, which, you know, if you're around here and you want to get your genome sequenced in 2 years or so when you're online, you should definitely do that. It's a place where, you know, a lot of different diverse backgrounds come together, and my background, for instance, has been in physics and engineering, information theory, computational neuroscience, and yet when I work at Halcyon as a director of analysis, I basically do electron microscopy, and I do automatic sequence generation, things like that. It's basically the best job I've ever had. Next to that, and you know, separately from that, I'm also the founder and organizer of the organization Carbon Copies, which is a network that brings together the experts and the projects that are needed to do substrate-independent mines, and to do road mapping and keep the roadmap updated for that. And I want to tell you today what that means. What does SIM, or substrate-independent mines, mean? What's it about? And also to make its feasibility very explicit. Now, there's a problem here, which is that the slides turn out to be rather dark on that projector. And I may turn off the light at some of the slides where I think the concept drawings are important to see. I really wish that this kind of software just had a little slider where you could elevate and lower the brightness. That would be really fancy, great feature to have on presentation software. So this conference really, its main topic has been about life extension, immortality, concepts like that. But just to bring that back to what it really means, what it's about, what are you really? I just want to kind of focus us back on that for a moment. So what I'm trying to show here, if you can see it, is that there are a number of different things that come together in what you are. One of them is your experiences. In the background there, I've got an image of a crew of the space station that's seeing the sun come up. It's also your body, so it's basically how you take in information and how it gets into your body, what you do with it, how you then act, how you impact your environment. And then there's all these characteristic responses, the actions that you undertake, your characteristic responses. All this stuff together is you. But what do you actually know about it? What is really the experience of being you? I can't even touch this because there are atoms here, electrons, neutrons, protons, the same in my fingers, but they don't actually touch. There's mostly space here. And electricity travels up my nerves, but I don't really know about that either. All I know is that something's being processed in here, and it's a combination of my awareness of input and my experiences, so my memories from previous encounters with input. It's my desires, my executive decisions, that sort of thing. That's really who I am. That's what you are. Those are the things that are there. So when we talk about how can we safeguard that or expand it, how can we do life expansion, there are really multiple ways of approaching that. Now, one of them is the one where you say, okay, so we've just looked at what sort of things affect that, your environment, your body. Maybe you have to keep all of those the same, maintain them, so that you can maintain yourself, your being. So you need to make sure that the environment doesn't change too much, so that our bodies are the right bodies for that kind of environment. We need to make sure that our bodies don't change too much. In other words, you may have to carry out rejuvenation, such as what Aubrey was talking about yesterday. And all of this makes sure that you can still exist, and maybe you can even improve yourself in some way. That's the maintenance approach. The other approach is that since we just discussed what we really are, maybe you can access that and deal with it directly. So what I'm saying is that what if we can get access to that information and deal with it the same way we would with a really important piece of information, like a program, for example. If you have an important program, what would you do with it? You would back it up somewhere. You would also want to have access to it, like open source, so that you can change the lines of code and improve it if necessary, or fix it if something's broken. These are the sort of things that you can do with what we call substrate-independent minds. The idea being you have access to the functions of mind, to that which is actually causing this experience of being that you are, and you can do things with it. You can put it on another substrate. That doesn't mean you don't have a body. It just means you need to be able to run on multiple types of hardware, let's put it that way. So then there's a question, well, which way do you use? Well, it's a matter of strategy. I mean, both things you should do. They're both really valuable. Sometimes you need to consider which one could come first. Well, if your background is in biology, you probably have a good understanding of what kinds of damage are occurring and which sort of therapies you could use and whether they can keep on improving, so maybe you feel confident about that. If you have a neuroscience background, then it seems to you that, well, yes, data acquisition is something we already do. We know how to get at those bits and pieces. Even if some of them haven't been cataloged and haven't been described perfectly, we know how to characterize them and describe them when we need to. So it seems like something that's doable. Now there are two other terms I just wanted to quickly describe before going on, which is mind uploading, which is a term that's been around in the transhumanist community for a while. It's a good term, but it's also a bit confusing because it doesn't really tell you what you're going to do once you've uploaded some data. Are you just going to put it somewhere in storage? And what about downloading, offloading, sideloading, all that stuff? So it's a bit confusing. And in the SIM community, we've decided that the way to use it is as the process. So SIM, substrate independent minds, is your objective. Mind uploading is the process. You take it from one substrate and move it to another substrate. Now there are different ways you could do that. How can you put it in another substrate? Well, one of them that I'm going to talk about more today is called whole brain emulation. That's a term that I came up with in 2000. It stuck, it expanded a bit. Neuroscientists are using the shortcut brain emulation now to talk about when they're taking neural circuitry and replicating it as well as they can. It's really the most conservative approach, but I'll tell you more about that in just a second. I'm rushing a little because I've got a lot of slides. So, as I said, there are many ways you can go about this, and two of them are the ones that are really being researched actively, and that's brain-computer interfaces and brain emulation. Brain-computer interfaces are very interesting because they eventually, when you try to increase the bandwidth, lead to the same problems that you need to deal with whole brain emulation, and they also have a good commercial incentive in the sense that at every stage you can build these. Now it's so interesting that I thought, well, let's just do a workshop on that in 2012, so I'm not going to talk about that today. Whole brain emulation is the one that we'll look at, and what are the four main things that you need to do to get that done? One of them is that you need to know the scope at which you need to work, and the other is the resolution. I will describe that in more detail in just a moment, so I won't go into it too much detail now. Then you need to deal with the structure of what you've got. So what are all the components, how are they connected? The structural connectome. Connectome is a word that comes from genome, of course, but it's applied now to the connections in the brain. Functional connectome, which is the characterization of the functions of the components that are there. And you need some sort of platform on which you can emulate, on which you can actually implement this new reproduction of what you had before. I do want to talk a bit more about these important issues of scope and resolution. See, every time you try to understand something, model it, reproduce it, whichever, you have to decide which level are you going to represent things at. What is the resolution that's important to you? And the really important thing to understand there is that the resolution you pick, at that resolution and below, you need to be able to characterize the components really well. You don't want to miss latent function, which means you need to be able to describe their function well. If you're looking at the everything that's above that resolution, you need to be able to describe how they interact together so that they produce an emergent function. This means you need to understand the connections between them, and you need to basically map them all out. So there are two things you can do to try to simplify your task. You can say, well, we can look at a lot of functions concurrently, and if we do that and we see which components are affecting other ones, then you can come up with what's called a functional connectome. So you just see how the functions propagate, how the activity propagates. The danger there is that if you're only looking at it for a short period of time, you can again miss latent function. Basically, you've chosen a really big black box and you're trying to describe everything that's in it. If you want to simplify your task, on the other hand, by looking at fewer different types of information, so let's say you don't want to look at function at all, but you just want to look at the structure, by scanning it really carefully and looking at all the morphology that's there and say, well, if we have a library that we can map to and say, this neuron looks like this, well, it usually has that function, so we have a probability distribution of what the parameters can be based on what we're measuring here. In principle, you could do that, but it relies on a few things. You need a one-to-one mapping, and we don't know for sure if that's there. Also, the problem is that if you have errors in your one way of measuring, and these errors all happen to be the same type of error, let's say that you're always measuring things just a little too small, then your simulation of that is going to have cumulative error that you're not going to get rid of just by using a neural network that is more robust. So, if you only have one measurement, that's a little dangerous. I think structure and function are both really important. Also, I think that if you're building something complicated, it's good to do it bit by bit. So if you're building up a piece-by-piece thing and you can keep on validating, that's better than if you build a big system and just press the green go button and say, okay, that's fantastic. Now, this is not just sci-fi. It's not something that's coming along in 200 years or whatever. And I want to make that very clear right now. So I'm going to talk about specific projects that are working on whole brain emulation right now. They're working on each of these parts. These aren't all of them, but these are the ones that I find really interesting, and I'm going to pick out two specifically, which is one of them about the structural connectome and one for the functional connectome, because I just happen to want to describe those today. But the other ones I'll quickly summarize. So let's say that you want to work on extracting the structural connectome. You want to find out all the connections between the different parts. One way you can do that, since you're saying you're looking at structure, is that you say, well, this is an observation of something spatial. So we want to look at it, say, under a microscope, like an electron microscope. Then what you need to do is you need to slice that bit of substrate that you have, like a grain, really thin and look at it under a microscope. That's one way of going about it, and that's one that I'll talk about a bit more. Another method is a biological approach. Let's say you want to infer the connectivity. This is a method that Anthony Zador is using right now, and in other labs as well. And the idea is you basically take little barcodes, like DNA strips that have a specific code. You use a virus to bring them to each synapse so that it drops one of those presynaptically, one postsynaptically, and then when you extract the neurons afterwards and you sequence everything that's in there, if you find the same snippet in one neuron and in another one, you've got pointers that are pointing to each other saying these are actually connected. So this is a biological way of getting the connectome out, and all it depends upon is really high throughput DNA sequencing. So, oh, how could Halcyon possibly help there? Well, that's something that seems really obvious to me. Now, if you're doing the functional connectome, again, there are several approaches. One of them is the idea, this is what I call generally a DMOX tree. The idea is that you're doing a hierarchical measurement, and you're taking the information out that way. One of the implementations that has been pioneered by Rodolfo Linas is the idea of nanowires that you can put in through the vasculature, and they sort of spread out, and they reach all the neurons, and they record from those. Now that last bit, getting to reach all the neurons, that has certainly not been achieved yet, but nanowires like this have been built. They've been built at the NYU Medical School, and so that's an interesting approach. There are some other ways of doing it, like only nodes and not edges in this DMOX tree, and using the existing structure, like the axons of the neurons to transport ultrasound or something like that as a communication method. So this is the DMOX tree idea. Again, there's also a biological variant where we say the interesting thing to do is to try to go down into very small sizes. And because we can't do that really well in other ways right now, but biology is really good at that, maybe we can make something similar to what I just talked about for the structural connectome by using molecular barcodes, like putting something on a molecule. And the idea that we're working on in collaboration with George Church and Ed Boyden and also Conrad Cording there is the idea that we could encode that on DNA by having, say, for example, it's just one example of a way to do it, have amplification of DNA going on, and every time there's a voltage event, an error occurs with that amplification. So when you then sequence and find the errors, you can see when events occur. So again, you plug out the neurons, you find all that DNA, you sequence it all. Again, that's a high throughput sequencing thing. And then the third one, which again, the slide is so dark, and soon I'm going to probably turn off the light for this, is the technological approach of getting to the small. So it's really both of those things. It's the node-only DMOX tree, but then using integrated circuits, and I'll talk about that more, so I won't go into it right now. Why is this not advancing? Oh, there we go. Okay. And then lastly, of course, it'd be nice if you had hardware that was better than a regular computer for putting your information on. So neuromorphic hardware, like the sort of thing that's coming out of the Synapse project, that would be really cool. So just let's get into that first one I wanted to highlight, about the structural connectome using the imaging approach. The reason I want to highlight it is because it's basically here now. We have the devices that can do this. In fact, Winfried Denk and Brigman, as well as Bach, both of those, they all published a set of really cool papers in Nature right now where they used something like this to show that they could map out the structure, do functional recording in the same bit, and deduce from the structure what function these neurons would have. This was in retina and the visual system, and in fact it could do this. So this is actually part of that validation, part of that work about scope and resolution that I was talking about in the first box. Now, the way that Winfried Denk did it was that he had a block of tissue, and he would image the top of it with an electron microscope, and then ablate the surface, go down a little bit further, and keep doing that. His method only works for really small volumes. But Ken Hayworth, who's a real advocate of whole brain emulation, worked on a machine that would do this for entirely large like the brain. So the idea there is you have something called the Adlum, this is first model, the automatic tape collecting lathe ultramicrotome, where it takes really thin slices, puts them all on tape. You see some rolls of tape over here. Eventually it's supposed to go on a wafer, and then you have a library of these wafers. You can do random access within that library, and follow things with an electron microscope, do all the mapping of whatever you want to do. So that's the idea of how do you do this with the whole brain. And yes, this device exists. Here's an example of a slice from and imaged with electron microscopy here at 5 nanometer resolution, so that you end up being able to see things like what you see in the red box there. That's where an axon and a dendrite are getting close together and the synapse is there. If you look where the white arrow is pointing, those are tiny little vesicles in there containing neurotransmitters. So at this resolution, you can even see how many vesicles of neurotransmitter are there, so that you can get an idea of what the strength of the synapse is when it's stored in chemical format, which is LTP. That's not our long-term memory. This is sort of intermediate term memory, sorry. And then you get these kind of reconstructions, which is the sort of work that Winfried Denk has been doing, publishing. So you can reconstruct the cells, you can reconstruct the connections between the cells, and by doing an electrical analog of these models, you can deduce what the parameters are when you're putting them into a model. And again, this is something that is here. I mean, the only thing that still needs to be done about this is extending it so that you can do it with the volume of the whole brain. Because right now, doing that for an entire brain takes a long time. It's difficult in that sense. But it's really just a technical issue. It is not that we need any new breakthroughs in science or any new understanding there. Okay, so this is definitely a point where we're going to turn off the light. See if that helps at all.
Kelly?
Here we go.
Just don't extract us from our seats, please.
I hit this one accidentally, so that seems to say the system. Okay, I meant to go light off.
Right.
Okay, well, before you can see it, I'll just talk about it anyway. One of the things that we'd really like to do is you'd like to be able to sit there next to every neuron and you'd like to be able to record information on it. That's what you really want. That's all the information you want to be able to get at in a functional sense, because then you can see how the neuron's function is changing over time and all of that. We can't really do that yet in the sense that we'd love to, which is basically nanotechnology, which the biological approach gets down to those sizes. And we're not very good at handling that yet. But what we're really good at working with is integrated circuits. That's something we understand. And so the concept here is let's not work at the nanoscale, let's work at the mesoscale, where basically we have these things that are about as big as a red blood cell, 8 microns in diameter. And what can we put on that? How can we functionalize those to get data from the brain? And if it's showing up, yeah, oh, but it's not showing right now. It's not there. Oh, okay. Oh, it's sort of visible. Yeah, if you, let's see, there's actually a pointer on here, isn't there? See this middle part here? So this is basically an integrated circuit. And on this, if you have an 8 micron diameter with the technology of 2009, Intel technology, you can put on there just as many transistors as you had on the original Intel 4004 CPU, which is a Turing machine. And you can power this, well, we'd love to power it with glucose, but we're not that good at that yet. But you can power it with pulsed infrared radiation. Basically, you've got solar panels. And here on the back, which you can't see very well, even in this darkness, is basically an antenna, because what we can do if we want to get information out from something passively without using a lot of power, we can use RFID technology. This is something that Yale McGuire and George Church thought of putting into these cells. And that's that you can use basically an infrared version of RFID. It's not at radio frequency to get passive information out. Now, if you use today's technology, 2011, then you can already put on that as many transistors as you had in the original CPUs that were used to guide cruise missiles, for example. So this is quite a bit of computational power. What you want to do then is encase it in something that makes it either biologically inert or biologically active if you want to functionalize it. Casings like this have been built. In fact, a lot of this stuff has been done already. There's a group in Spain that already put integrated circuits inside cells without disrupting the processing of the cell, without disrupting the cell's necessary functions. And these kinds of things, like, for example, artificial red blood cells, have also been built. So this is not future technology, once again. Now, the problem is that that's still not what we really want, because we'd like to have things that are flexible so that they can be not just inside the capillaries of the vasculature system, but we'd like to be able to put them straight in the cerebrospinal fluid or fit between cells. So we'd really like to work with smaller bits and pieces as well, which we can, because we can subdivide this into little bits that are 2 micron or 1 micron diameter and still have some function. The issue then is that you want to use a team approach. So again, this is this hierarchical thing that we saw with the demox tree, where you have, say, a hub that takes care of communication to the outside and communication between agents, and you've got smaller agents that do things like sensing, stimulating, maybe even hurting others, doing navigation tasks, and you can even imagine that they might do some morphological mapping internally. What you really have is an access system. So what we have here is this idea that inside the system where you have the brain, you've got this secondary set of devices going on, a cloud of computation basically, that can do things like stimulate, sense. Here we have one that's been functionalized with nano Velcro. It's another thing that's already been invented, in fact, by the same Spanish team that also did the insertion of the cell into the cell. So the idea is you have this thing operating in parallel, and if you need to detect some other signal you hadn't thought of before, these agents can help you get that stuff there. You can deliver compounds as well, for example. So this isn't really that crazy. It's not that difficult to do. This is today's technology. Now the nice thing about this is if you take those at the size I just showed you, and you need to put one agent next to every neuron, and you want to have, say, hubs, one for each of 8 agents, then the total volume that you consume is about 1 cubic centimeter, which is, for all the neurons in the brain then together, it's only 1/1700th of the volume of the brain, so it's not really that disruptive. And if you want to co-register between your structural scan and your functional scan, there are different things you can do. You could use an approach where you find the relative distances between agents and use that in some fashion. You could also leave the agents in place and run it through an athlon, for example, and find those cells still embedded in the brain so that you know exactly where they were. Of course, in that case, it's no longer in vivo. Now, the only thing I want to say about this, I'm not really making any predictions here, is that what we're talking about are projects that are really concrete. And this is something that you can therefore plan for. It's something where you say, okay, we need to do this, this, this. We've got multiple steps. We can try next year to first build a simple one that is a little larger, and we put it in animals, test it there first, and build another one. If you have a plan like that, it means that you can allocate resources and decide how long do you want this to take. The more resources you allocate, the faster you get done. And then I just wanted to say a few things because, I mean, I was impressed with Jan's talk this morning about the matter of extinction risk, which was a term that Max Moore used rather than existential risk, and I think it's a good one. The first point I want to make about that is that this is a problem that we face already. The status quo is not one where we're safe, basically, because we're only good at living in this environment. We're good at living in this time. Like when things change, like say you've got an impact of an asteroid here or meteor, or you've got a huge biological plague, these sorts of things can happen, and they're dangerous to us. So what we'd like is to be able to adapt to those kinds of problems and be able to deal with them in some way. Now, the idea that we could use artificial intelligence, general artificial intelligence, to help us with that, it's not a bad idea as such, but it's true that it's very difficult to control what we want it to do. For example, as I think it was Jan already pointed out, the US Air Force has this plan that they want to get rid of pilots. And in fact, when I spoke to them, they said that by 2045, they basically wanted to have Skynet operational, that kill decisions could be carried out without human intervention. Now, is that a really smart idea? Okay, that depends. Do you really trust your AGI? But if you want to set up a bunch of rules so that you can be sure that nothing's going to go wrong, you want to make sure everyone is working according to a plan where they understand the dangers and they don't do the wrong thing. This is also difficult. First of all, how do you control what different people actually do or want to do? Because you can't really look in their minds and see what their ulterior motives are. Plus, they may not know what they're doing. As Jan pointed out, it's not necessarily the most advanced AI researchers that are the problem. You have a whole scale there. But if we're only dealing with an abstract problem, it's very hard to define where the danger lies. It's easy when you're thinking in abstract terms to worry about basically everything, because any scenario can seem plausible. Are the programs we're writing today safe? Maybe not, because maybe together somehow they form something that happens to be intelligent enough so that eventually, if we have enough of that and put all those narrow intelligences together, we end up with an AGI. And currently, there's so many projects going on already that could lead to AGI. So it's very hard to imagine how you can actually corral that kind of organization, and then you've still got the superbug problem, which is if you're trying to put in a lot of controls, if you're trying to make sure that nothing breaks out and becomes the dangerous AGI, then the only ones that are going to break out are going to be the ones that are the most cunning, the most stealthy, the most powerful, and there won't be any, less cunning, engaged, or stealthy ones to stand in their way. So I'm not sure that I'm really that happy with that solution unless someone can explain to me exactly how you would do it. This one here, we do know how to do it. We know that we can do open emulation. We've seen that there is a path to do this, that it's actual projects that are already underway. And it means that, what we can do is we can give ourselves the ability to be at the level where we need to be to A, back up, be fault tolerant, catch up or keep up with developments in AI. It's the idea of a balance of power, that right now, the reason why we haven't wiped ourselves all out is because we keep each other in check to some degree. Now, I'm not sure that it's fail-safe or foolproof, but we have seen it in operation. And it only works for the dominant species. It doesn't work for anything that is, less powerful, let's just say, because what do gorillas have to say about us? So really, I think that that's why I'm advocating that this is a good approach, because it means we're dealing not just with the universal Darwinism, so basically all the other challenges and competitions that are going on and being flexible for them, but it adheres to at least some principles that we've already seen in action, this balancing power idea. I'm open to discussing it, but that's currently my view. Thank you very much.